Our next talk is from Haaren at Intel, and it's titled Next Steps for Software Data Path.
Thank you, Ben. Hey, folks. My name is Haaren, for those of you who haven't met me before. I'm working for Intel, and I'm primarily focused on optimizing the software data path in OVS. So quite generically, just trying to make it go faster, really. Let's have a look. Perfect. So if we look at OVS performance from a really high level, and I call this my marketing slide, good is to have more performance, right? Higher performance. But really, if we're trying to achieve greatness, what we need is this kind of batteries included experience, right? We need this to be easier to deploy. We want it to be easier to integrate. We want all of the developers in the community to get that performance for free for easier. That's kind of what we're really going for. So some of you might remember from last year, I'd done a talk where we talked about the DPCLS, so the data path classifier or the wildcard matching engine inside OVS. I talked about a SIMD version of that, so single instruction, multiple data. It's a CPU technique, low-level stuff for essentially accelerating OVS's wildcard searching engine. And we talked lots of colorful pictures and details on how we can really accelerate packet processing performance using those. And the rest of my talk here is kind of looking from that point of view of performance. So previous slide, performance is good, but really we need this batteries included experience. And that's what I'd like to focus on for the rest of the talk today. Cool. Okay, so if we want to talk about like this batteries included kind of experience, what does that actually mean? And for me, it means a few things. So we need the test and validation to be present for those code paths that we're optimizing. We need to have the same confidence in our existing code paths as in these new flavors or new versions that have more optimized versions of that code or performance, basically. We want to talk about usability and debugability, because if we can't easily deploy this and debug this in the field, then it's essentially not making the OVS project easier to consume for real-world deployments. So we kind of need to look at it from those angles. And then finally, we need to actually get those optimizations and these changes packaged and deployed in a data center somewhere so that the people actually running OVS in the end benefit from that. So we'll kind of take those topics one by one and have a look at each one individually. So if we want to talk about testing and validation, we're talking about a number of different things. And in the context of the performance talk from last year, there's a version of DPCLS that uses these SIMD instructions, or AVX 512 for the particular version that I discussed last year. And what that does is it uses a particular CPU ISA feature, so instruction set architecture, or instructions that CPU has available to it, and uses those to do the processing of the packets themselves. We can do that in multiple different ways. Please refer back to the talk for all the fun performance details. I'm going to try and lay low on the techie detail this year. What it really means from an OVS deployment point of view is that we have two implementations of approximately the same functionality. So we have a scalar code path, and that's really the one that we have upstream today, and that's doing your wildcard matching in deployments. But we also have another optimized code path using other ISA or CPU features to do that same type of work. And I kind of represent this in the diagram on the bottom right, where we have the scalar version and an AVX 512 version of the same function. And if we want to do testing and validation, we don't want to have to, increase the size of our test matrix times by 2 just because we now have 2 implementations and that you guys need to go and validate things twice. That doesn't scale. It particularly doesn't scale if we start adding 4 or 5 different optimized versions, right? Then you get this absolute crazy explosion of test and validation. Not going to fly. So what I'm proposing here is that we look at this from a more automation point of view, from a workflow point of view, and we start getting a bit smarter about our automated testing. And what that really means is we're going to build a DPCLS instance or an implementation of the DPCLS subtable lookup function. And what we're going to do with that is we're going to hijack it and use it for testing all of the other implementations. So instead of going directly from one of the DPCLS lookup function here on the top left, directly into an implementation of that lookup, we're going to be on the right-hand side of the diagram here where we have the testing, and we're going to go from the DPCLS lookup itself, we're going to go down to the testing implementation of that DPCLS subtable search function, and we're going to check the scalar version, we're going to check any optimized versions with AVX 512 instructions or otherwise. And we're going to compare the results. We're just going to check, is the output of every single classification for each packet in the scalar code path the same as the AVX 512 code path? Because if it is, it means that those 2 implementations are equivalent. And the nice thing by doing this is we can run the entire unit test suite that OVS has with this testing mode enabled, and you will test absolutely all of the existing tests with both of those implementations, essentially without any manual human effort required. So your testing matrix doesn't explode, but you do get that benefit of testing every single implementation all the time. So it gives you confidence in all the different implementations, and it doesn't cost you human, like manpower, man time. So that's kind of one of the things that I'm looking at from a performance optimization point of view. We need to really understand test and validation, take those concerns into account, design for that by building this DPCLS tester implementation, plugging in all the different implementations of the actual like lookup search functionality, and then run that with all the unit tests. I'm going to break the conference rules here a little bit and say, any questions at this point? So I'll do questions in line. If people have urgent things they want to know, just stick a hand up and I'll try and get to you. Cool. Moving on. So we've talked a little about test and validation, but equally so important is being able to use and understand this, to be able to debug it if something seems to be going wrong in the field. You want control over these various features. So easily being able to view the status of, is this optimization currently in use or not, is kind of one of the prime candidates of something that, you want to know which implementation of the DPCLS is being used in that production. Are we running the scalar code path? Are we running an optimized version of the code? So easily understand what optimizations are in use, and equally so provide some feedback to the OVS community. So last year I rambled on a little about trying to get more feedback from people actually deploying OVS and understanding what performance concerns they have, understanding what subtables they're deploying, understanding what their DPCLS performance looks like and where their bottlenecks are. Because for folks like myself, to optimize against those, it's really useful to have that data. So big encouragement for anyone in the community, if you do have some performance results or concerns or a particular deployment that you'd like to see accelerated, please reach out either to the OVS mailing list, feel free to CC me directly if you prefer. So yeah, open call for data on what subtables you're running in your data center. So that's the easily view the statistics, but equally so we want to enable power users or people who are more familiar with OVS deployments to actually configure things. So somehow someone will require to be able to set a very specific version of a subtable lookup function. So you may want to reset to the scalar version because that's just the default and then let's say the one generic implementation that will work for any subtable. But what if you wanted to replicate an exact deployment that some customer has in the field and you need to use exactly the AVX 512 or an AVX 2 version of that function? So these are things that we need to provide those hooks to power users to be able to run an OF kettle or dpctl command to actually set that particular implementation. So again, these are things that we kind of need to design in from the start. So very loosely here on the left, again, we have a little diagram. The user wants to be able to easily understand what's going on, so we need to provide some commands to provide to allow the user to introspect or kind of gain some knowledge of the system. There's a talk later on today. I think Ian is covering some of the subtable bits topics, so I'm not going to go into detail on that now, but I do encourage you to look at that talk later on. On the right-hand side of the diagram, we have the power user, where we want to be able to set or modify the configuration of OVS. So in this case, we want to change the DPCLS behavior possibly from an optimized lookup function back to the scalar version. So that's what's represented in the diagram there. If we move on, what we really also need in order to get that kind of batteries included experience is to have that packaged and deployed. So up until now, we're talking relatively about code changes, about testing, but ultimately, if it's not going to transparently run whenever you deploy it, then like if it requires manual effort to try and deploy this specific version of an OVS binary, that doesn't fly either. So we really need this to scale across all of these pillars, really. All these different angles need to be resolved in order to have this be able to be upstream and easily deployed. So in order to make use of these types of ISA-based optimizations, again, this is down to a specific instruction set that a CPU has, we need some runtime flexibility in the code base. That was actually added in OVS 2.12, so the August release, where we added a function pointer at the DPCLS subtable lookup location in the code, for those familiar with the code paths. And that gave us that flexibility to start being a bit more, a bit more flexible in what function does the actual lookup. And as an end result, we could specialize versions of the scalar code and get more performance just by having this function pointer there for flexibility. So no ISA-based optimizations present there yet at all. However, if we want to look further and get more performance, which we can, then we need to start looking at runtime CPU detection. And what I'm really saying here is that when we deploy an OVS binary, as a packager, you want to compile that binary once. You want to be able to deploy it on any machine in your data center, and you want it to operate correctly. That's the default, right? That's our baseline. If that's not there, it's broken. So we want to have one binary that can be deployed on any machine that will function correctly. But equally so, if we have a modern CPU, perhaps a Skylake or Cascade Lake, where we have these new ISA capabilities, then you want to make the most of your CPU. You want to use those capabilities to gain more performance. And that's what this runtime CPU detection will ultimately allow us to do, to make the most use of the features that are present in any given CPU and to actually use that ISA capability for performance. So that relies initially on the flexibility. So flexibility was brought in the last release. That's why I'm not calling it out as much here. But here we're really talking about packaging and deploying that. And we need to enable that at runtime. So this is one area that OVS, today, I'm not aware of any part of the code that is making decisions on what functions to use or what implementations to use based on the ISA. And I'm getting a head shake here in confirmation. So this would be, in a way, a novel area for OVS to look towards optimizing. And for those who think this is some kind of black magic or so, if you've ever deployed DPDK, you've already used this. DPDK does this across the board with the PMDs to understand if the vector routines should be used, yes or no. So these concepts are not new in the industry. They are perhaps new to the OVS codebase, but they are well tested, well deployed. They exist across the industry to use function pointers and some kind of CPU feature detection to make choices for where to point that function pointer. So that's kind of what I'm suggesting here, and I have an RFC kind of V1 patch. It's relatively trivial to do, actually. There's less than maybe 100 or 150 lines of code or so in total to achieve this. But the question that I pose to the community here is what kind of approach do we want to go? How far do we want to take this? Do we want to make this an OVS kind of first-class citizen, that we have a new component in OVS that's called, we check what CPU flags we have, and we provide OVS APIs to do this? Do we want to reuse some of the DPDK implementations thereof? So DPDK does have features and functionality to check all of these things. Do we just want to reuse that and then we're pretty much done? So that's kind of an open question. What I'd like to do is post this patch on the mailing list. Anyone interested can have a look. Feedback welcome, as always, on the mailing list. So that's kind of the next steps that I'm proposing for this particular area. So what the benefit of that is really that you get one binary which is going to run everywhere. So on an older system, we'll continue to behave correctly. We will point that function pointer at perhaps the scalar version of the DPCLS implementation that will allow us to run anywhere, to always give the correct and same performance as today. There won't be any performance degradation due to doing this. And if you deploy on a machine which has a newer ISA or newer capabilities in the CPU, then we can optimize against that. And we can start doing some really interesting things. So that's kind of the packaging and deployment area. This does, however, require some build process updates. So what I mean here is today we compile all of OVS. Every file in OVS is compiled with a -m arch, for those familiar with compiler flags. So an architecture of, I think it's a Core i7 that's used in many of the packages. And that limits the compiler from emitting instructions that are newer than Core i7. So anything that goes up to Core i7 is fine, but anything newer, the compiler is not allowed to emit in the instructions, because that would or could cause an illegal instruction exception on any specific platform that doesn't have that. So what we'll need to do is to compile specific files in OVS, so not everything, but very specific files with that have these DPCLS implementation optimizations with newer flags, and only choose that run path at runtime, essentially. That function pointer will get set at runtime. So for those interested in the real techie details on how this works, please do come find me. I'll be around for lunch and around tomorrow as well. So I'd be more than happy to talk all the techie details. I'll try and keep it kind of short and sweet in terms of techie here. But from a bigger picture, the build process in OVS will need some changes. And in the packaging scripts, perhaps from the distros and the people actually building, .debs or .rpms for OVS, that we'll need to have a discussion around that and to understand and to see how we can best make use of those things. So that's kind of the diagram on how this CPU works. Without the ISA on the left, we can probe, do we have this AVX512 capability in the CPU? If we don't have it, then we just use the scalar version on the left-hand side. no problem, everything works as it would today. If we do have the ISA, however, then this DPCLS lookup function can call directly into the AVX512 implementation thereof, and we just get the performance benefits from it. Again, referring back to the very start, we have an automated test suite at this point that's validating that all these implementations provide the same results, which gives us the confidence that it doesn't matter which one is chosen at runtime, because all of them will actually do the same packet classification or give you the same results, even though how they implement it internally may be different. Question, one moment.
I was just curious. So people who are making maybe local changes then may not have the ISA. So then I assume then you're just going to depend that later on that part of your CI/CD will detect that there was some sort of breakage because compatibility changed somehow, or that it was extended in some way that doesn't support the new features.
Thank you. Good question. So ultimately, whenever we define one of these, kind of the green arrow in this picture, really the one that moves, at that point we have a particular function call that's passed particular arguments, and the behavior of that function is well defined. In this particular case, for the subtables, you're given a bunch of keys, a bunch of rules, a bunch of other like pieces of data structure, and you're expected to match those against a particular DPCLS instance. So because there's a well-defined point in the code where a specific operation is expected as the result, I think that there's little breakage expected. You're absolutely right in saying if there is a change in that API, if something does change, and somebody makes a change in the scalar code and not in the various vectorized implementations, there will be breakage across those. Absolutely correct. It is something to be concerned about. So the points to choose where we put these function pointers should be places that have a well-defined API. And ultimately, that's, I think, in the case where we got the subtable lookup function from a DPCLS, I think that was a very good choice, actually. The API there is very well defined, or like the semantic of what that function should perform. And equally so in future, if we want to look at this optimization and apply it to different areas of OVS, then we need to locate a similar position where there's a very well-defined semantic of this function is going to perform this operation on those data structures. And then that's what you optimize against. Because they're relatively primitive components or parts of the OVS pipeline that have been stable for a number of years at least, I don't expect much change. So for example, miniflow extract takes packets and parses them into miniflow data structures. That operation as a whole, we could kind of classify as miniflow extract. I believe there was a talk this morning on doing that in Rust as well. So similarly, that has a specific function that we just need to go and perform. But good question, and thank you. Yeah.
So there's a valid use case of OVS running inside a VM. So for that use case, how will you solve this kind of runtime CPU detection? You may not have access to the physical CPU information.
So I believe that whenever we emulate a CPU as a virtual CPU, we actually do get, like we can run the CPU ID instruction on x86 and x86-64, and that will return to us what CPU flags we have. Now, to your point, we may be running on a really modern CPU, but the CPU flags in the VM may be told to pretend that it's a much older generation CPU. And in that case, OVS will just use the scalar code path. It will see its limited feature set from the CPU based on the virtualization and not use the latest ISA. If the virtual machine, however, is configured to pass in the native type through QEMU, I think there's a particular flag you can say -m CPU equals native or so. Then it will pass its native CPU flags through, and you will get all the performance benefits of the right-hand side of this diagram. So it scales to virtualized use cases is really what I'm saying. Yeah. Good question, though. Thank you. So if we kind of want to start summarizing a little bit and keeping an eye on time here as well. I've talked a bit about validation and that we need some kind of test implementation for the various DPCLS functionality. I've talked about usability, and there's a talk coming up later in the conference on that, so I'm not going to labor that one too much. There's some debugability that we need to resolve, that in deployments we can actually provide users with the information they may need to provide other people with to debug certain situations. And we've provided power users with a method to specify or to emulate a deployment exactly to be able to resolve issues with specific deployments, perhaps. And we've talked about packaging and what changes are needed for the CPU ID-based optimizations or ISA-based optimizations, really, to do that. And I kind of see those as well as flexibility, which I mentioned earlier, but isn't really listed here as that's already been achieved for the DPCLS work. So validation, usability, easy to debug, packaged and essentially ready to deploy, as well as flexible code paths in the OVS codebase are kind of the pillars underneath this performance optimizations. So without all of these kind of covered and well understood and designed into our optimized solution, the performance optimization isn't ultimately going to land in the data center and accelerate your workloads. So really what I suppose I'm suggesting here is over the next months, I'll start trying to bring some of these changes to the OVS mailing list. I'd love to see your input, to see any concerns in particular. If there's any concerns around any of these things, please do come talk to me before the end of the conference. A lot easier to chat about this in person than on a mailing list. But otherwise, the mailing list is fine too for people. If anyone has questions, please let me know. So that's the last slide. I have a thank you and questions, and my email is here. So if anyone wants to drop me a line directly with questions or CC the mailing list, that's perfectly fine too. I'll leave this diagram up, and if there's any future or more questions on any of these topics, please let me know.
Thank you very much. Yeah, I have a question about the. I know some compiler can generate the SIMD instruction automatically. I mean, sometimes the scalar code should be the C code, right? Can be generated into the vector code. So do you test or try some auto vectorization for the scalar code? And what's the difference about the performance?
Very good question, thank you. So the question in summary is, do we try auto vectorization? And if so, what is the performance benefits? So unfortunately, the way things are packaged today, we limit the compiler in what it is allowed to use for vectorizing. So when we say that the march equals Core i7, for example, which I believe is the one that's used commonly today, we limit the compiler to only using 128-bit wide registers, even if larger ones are available on the CPU. We limit the instruction set to anything that was present at Core i7, which, if we compare that to the instruction sets that are available today, is quite limited. In order to address your question on auto vectorization, basically the compiler isn't allowed to do a lot of vectorization, and particularly against the more modern ISA, because we explicitly tell it not to. And that really comes down to this packaging, the last pillar here. In terms of auto vectorization and manual vectorization, possibly using these intrinsics, my experience has been that if we look at the way compilers auto vectorize, it's not quite as efficient as manual optimization. A very good example in this case is the DPDK poll mode drivers. So if you look at the RX and TX paths of certain optimized drivers, they use a lot of these intrinsics, and they go really fast for that reason. And the presentation I done last year on the DPCLS with AVX 512 was also handwritten in intrinsics, so coding these things manually. But in doing so, we can achieve much higher performance than a compiler could do, because as a human, we understand the work that's happening, and we can take certain assumptions around that. And those assumptions may not always be valid for the compiler. So the compiler, although auto vectorization, for certain use cases is very good. For HPC, auto vectorization is fantastic. For packet processing, the workload is just that little bit more complex and makes it harder for the compiler to generate the same efficiency of code as a human would be able to do. So very, very good question, though, and something we should probably chat more about, because it's interesting. All right, if there's no further questions, thank you very much.
Let's thank our speaker. Thank you.